Recording in progress.
Hi students, in this lecture I am going to discuss problems. Let us see first one, and before going to that let us see once what we have discussed. So first law dq equal to du plus dw known as differential form, or q equal to delta u plus w. Q is positive if heat is given to system, negative if heat is taken from system. Q nc delta t, it is a path function, and where C is molar heat capacity, which depends on the process, like isobaric Cp, isochoric Cv, right? So depending on the process. And W, in that W is known as work done by the system. Okay. So it is a positive if gas expands, and negative if gas compresses. It depends on again the path. And delta U, change in internal energy of the system. It depends only on initial and final states. It is a state function. It does not depend on the path. This is important point. Whatever may be the path, delta U simply depends on initial value and final values. Okay. The meaning of state function, and given by NCV dt. And many students having a confusion here. It is only for constant volume. It is not like that. It is valid for any process, not only for constant volume. Okay. Next, focus on problems. When an ideal diatomic gas is heated at a constant pressure, the fraction of the heat energy supplied which increases the internal energy of the gas is. Given ideal diatomic gas providing heat at a constant pressure. Okay. So what fraction of the energy is converting into internal energy of the gas? This question is asked in 1990 for 2 marks. Let us see how to get it. So condition is given that isobaric process. So P constant. P constant. Now write in first law. Q equal to delta U plus W. Since it is now constant pressure, Q value is NCP delta T. And coming to delta U, for any process, it is for any process NCV delta T. Okay. Now we have to find fraction of heat energy that converts into internal energy. That means we have to find delta U by Q. That is equal to Cv upon Cp, which is equal to 1 by gamma, right? This is now fraction, right? And given it is a diatomic gas, for diatomic gas, gamma value, for diatomic gas, gamma value is 7 by 5, right? For mono 5 by 3, for diatomic 7 by 5, and for polyatomic, it is 4 by 3, right? Now take this value here. 1 by gamma, it is 5 by 7. Wait, I have taken reverse. Gamma 7 by 5, right? It is 5 by 7. If they ask like percentage, okay? If they ask like, see for our question, this is answer. If they ask percentage increase, then we have to write delta U by Q into 100. That gives percentage change. Suppose in the same question, if they ask like, what fraction of the heat energy converts into work done? Okay, already we have seen this is 1 by gamma fraction that converts into internal energy. Remaining will be W by Q. That will be how much means 1 minus 1 by gamma. This is a fraction of heat energy that converts into work done. That means in this problem, that value will be total value 1. This is now 7 by 5 means 5 by 7. Remaining is now 2 by 7. This is a fraction of heat energy that converts into work done. Okay. Let us focus next problem. An amount Q of heat is added to a monoatomic ideal gas in a process in which the gas performs a work Q by 2 on its surroundings. Given that gas performs a work Q by 2 on its surroundings, find the molar heat capacity for the process. So this question is from H.C. Verma. So Q amount of heat is given, work done Q by 2. See how to solve the problem. If you want, you can try once of your own. So first of all, write down first law. Q equal to delta U plus W, and condition given that half of the given heat energy converting into work means utilized for doing work. So remaining is now delta U. That means delta U value Q by 2. Okay. Given ideal monatomic gas, and see what is a Q value. Q value is given by N C delta T. So here we have to calculate C value, and you can say here delta U is always equal to NCV delta T. This is for any process. Okay. And since it is given monoatomic, the value of CV for mono is 3 by 2 R, right? Substitute that here. That is equal to N 3 by 2 R delta T. So in the place of Q, or what I can do here, cancel 2 and 2. So in the place of Q, 3NR delta T. Substitute here. This is equal to 3NR delta T. Check it once. 3NR delta T. N delta T gets cancelled. N delta T gets cancelled. Remaining is now C. So C equal to, it is a 3R. Okay. It is C equal to 3R. So like this directly we can solve it. Let us see next problem. An ideal gas is taken through a process in which the pressure and the volume are changed according to the equation P equal to K into V. So here K is a constant. Show that the molar heat capacity of the gas for the process is given by C equal to CV plus R by 2. So it is given P equal to some constant into volume, right? So we have to show that molar heat capacity for the process is. Let's see how to start it. So given that P equal to K into V, where V is a constant. From this we can write it is a P V power minus 1 equal to constant. And if you remember that, we have discussed a polytropic process, P V power x equal to constant, right? That means now in this, x equal to minus 1, right? So writing now, it is in the form P V power something equal to constant. It is now minus 1, right? And for polytropic process, we have derived that C equal to Cv plus R by 1 minus x. Now see carefully here. It is Cv plus R upon 1 minus x value minus. That means 1 minus minus 1. It is Cv plus R by 2. Right? It is a direct one. Let us see next one. Right, see the question. At 27 degrees centigrade, 2 moles of an ideal monatomic gas occupied a volume V. Given temperature and volume, the gas expands adiabatically to a volume 2V. Calculate. So it is given ideal monatomic gas, initial volume V, final volume 2V. So volume is doubled. Given initial temperature, so we have to calculate now final temperature, change in internal energy, work done by the gas during this process. See, by seeing this, what we can say, volume doubled. Volume doubled means it is expansion. So expansion means work done by the gas is positive, right? Since it is an adiabatic process, no heat is given to system. So this work is done at the cost of its internal energy. That means internal energy will decrease. Therefore, change will be negative. So change is negative. Change negative means final temperature must be less than initial temperature, because we are knowing that internal energy depends on temperature, right? So volume increased, internal energy is decreased, right? That means temperature must be less than the initial value. Let us now calculate. So first write down given data. So given that T1 27 converting into Kelvin, 300 Kelvin, T1 volume V1, that is V. Final volume we have to, sorry, final temperature we have to calculate. Final volume given, it is 2V, and process is adiabatic. Process is adiabatic, and given it is a monoatomic gas. Mono means gamma equal to 5 by 3. Right, finding T means C1's relation between temperature and volume. So we have learned P V power gamma equal to constant. Next, T V power gamma minus 1 equal to constant. So we have to use now T V power gamma minus 1 equal to constant. Let us see. So I can write here T2 into volume 2B whole power gamma value 5 by 3. 5 by 3 minus 1. It is 5 by 3 minus 1 is 2 by 3. That is equal to T1. That is 300 into V power 2 by 3. That means T2 value. So V and V gets cancelled. Remaining is now 300 upon 2 power 2 by 3. Okay. And that value comes out to be approximately, it is approximately equal to 189 Kelvin approximately. Okay. Next, see what else we have to calculate. We have to calculate now delta U. Delta U means delta U equal to N CV delta T. Right? It is given now 2 moles. Right? 2 moles of ideal monoatomic gas. So N value is 2. Since it is now mono, CV value 3 by 2 R. It is 3 by 2 R delta T. Delta T means final value 189 minus initial value 300. Okay, 2 gets cancelled and taking R value 8.314. Then see what we get. So value will be approximately, it is minus 2767 joules. Okay, it is 2000. This is 7. So 2767 joules. And next question is work done by the gas. And we are knowing that for adiabatic process, Q value 0. That means delta U is equal to minus W or W equal to minus delta U. We got here delta U value. Therefore, W will be minus delta U. That is equal to 2767 joule because expansion. That means work done is a positive. Okay. So anything else they can ask in this one? Given we got now temperature, volume given, they can ask about pressure, right? By giving initial pressure, asking final value how much, right? See next problem. Right, so the question given. Calculate the work done when 1 mole of a perfect gas is compressed adiabatically. The initial pressure and volume of the gas are 10 power 5 Newton per meter square and 6 liter respectively. The final volume of the gas is 2 liter and molar specific heat of the gas at a constant volume is 3R by 2. At constant volume 3R by 2. Its meaning is it is monatomic gas, right? Given adiabatic process, adiabatically compressed. So we have to find work done. Compression means work done will be negative, right? Okay, first see how to start the problem. First write down given data. We have to calculate work done. It is given that process is adiabatic Adiabatic process, initial pressure and volume. P1. P1 given as 10 power 5 Newton per meter square. Initial volume, and that is given as 6 liter. And you are knowing that 1 liter equal to 10 power minus 3 meter cube. That means it is now 6 10 power minus 3 meter cube. Initial volume. Final volume is, that is V2. Final volume is given 2 liter. That means 2 10 power minus 3 meter cube. Okay. So this is a given data and given CV, right? CV value. CV equal to 3R by 2. So this is a given data. From this now we have to calculate work done. In adiabatic process, work done is given by, it is equal to 1 upon 1 minus gamma P2 V2 minus P1 V1. P1 V1. Are writing same thing as 1 upon 1 minus gamma. It is NR delta T, means T2 minus T1. Now see which is suitable for this one. We are knowing P1, V1, P2 is given. So first we can find from this given data what is P2 value, right? We can find what is P2 value by using P V power gamma equal to constant, right? Or do one thing, can we solve in a different way? Pressure, volume given. Also we are given 1 mole, right? 1 mole means, do one thing. Let us take gas equation PV equal to nRT. Pressure is known, volume is known, volume is known. Now, number of moles, it is given 1. So we can find temperature, right? I think this better one is, directly you can find T1 and T2, right? But again, problem is here, P2 is not known. Okay. That means we have to find P2 value, right? Without knowing P2, we cannot solve the problem. Okay, let us take P1 V1 power gamma is equal to P2 V2 power gamma. P1 10 power 5, V1 it is 6 10 power minus 3 whole power gamma, that is equal to P2, that we have to calculate V2 2 10 power minus 3 whole power gamma. Now see here what we can do. 10 power minus 3, 10 power minus 3 gets cancelled, right? And this is taken as 3 into 2, right? 3 into 2. Therefore, 2 also gets cancelled. Remaining is now P2 equal to, P2 equal to, P2 equal to 10 power 5. Remaining is now, this is 3, 3 power gamma, gamma value. Since given CV value 3R by 2, CV value 3R by 2, gamma value, it is 5 by 3, right? Gamma is 5 by 3. So it is now 3 power 5 by 3. Then C, pressure becomes now approximately 6.24 10 power 5 Pascal. Okay, it is approximately 6.24 10 power 5 Pascal. Right. Now using this in this one, P2 V2. P2 is known, V2 is known. In the same way, P1 V1, they are known. Substituting the values in that, then we get the answer. You can check once the calculation part. That answer is approximately 972 joule. The remaining part is only substituting P2 V2, P2 V2 minus P1 V1 in this one. In the place of gamma, it is a 5 by 3. Just substitute values there. Since it is now compression, the value comes out to be negative. Okay. Like this, we can solve problem.